So, so what is the drift speed of the conduction electrons in a copper wire with radius r equals 900 micrometer when it has a uniform current I equals to 17 milliampere? Assume that each copper atom contributes one conduction electron to the current, and that current density is uniform across the wire cross-section. So actually, this assumption might not be correct, but we just make this assumption to make things easier. Well. So actually, we need some constant from the appendix F. So this is the density of the copper, which is 8.96 gram per centimeter cube, and the mole mass of copper is 63.54 gram per mole, and this is the Avogadro number. And actually, you have learned it in high school chemistry class. So here we use this equation. We use this formula to calculate the number of atoms per unit volume. So within a millimeter cube, what is the number of the atom of the copper? So that as long as we know the number of copper, we know the number of conduction electrons. So here, the number of atom per unit volume equals atom per mole, which is this one, and number of atom per mole, and then we have mole per unit mass, and then we have mass per unit volume. It's just like the chain rule in calculus class, but actually this is not. It's just a ratio. So we have atom per mole, mole per mass, mass per volume, so that we have atom per unit volume. So here we just substitute the number into this formula. So atom per mole is 6.02 times 10 to 23rd power, and then mole per mass, which is molar mass. Molar mass is the inverse of this number, which means that the mass is 63.54 gram per mole. But actually, we want a kilogram rather than gram, so we need to convert it to kilogram. And then we multiply it by mass per unit volume, which is 8.96 times 8.96 times 10 to the third power, because we need to convert it to meter cube, we need to convert it to kilogram. So this one we need to multiply by 10 to 6th power, and this one need to divide by 10 to the 3rd power, so that we bring 10 to the 3rd power here. So we can calculate n to be 8.49 times 10 to 28 power meter minus 3. So there are totally 8.49 times 10 to 28 atom within 1 meter cube. So the drift velocity, the drift speed would be J over NE. then we know that J is I over A, so we have NE A here. So the current is 17 mD, so 10 to the third power, and then over N is 8.49 times which times 10 to 28th power, and then E is 1.6 times 10 to minus 19. And then the area is pi r square. Pi r square is actually times pi r is 900 times 10 to minus 6 square. So the answer will be okay, so I write it here. So it will be equal to 4.9 times 10 to minus 7 meter per second. So it's very, very slow. It's very, very slow. Consider this number. The absolute value itself is not very important, but actually you need to have some idea what is the order of magnitude. So 4.9 is not very, very important to really understand it. But actually, 10 to minus 7 meter per second is a very, very slow speed, which means that for every second, the electron moves 10 to the minus 7 meter. So it is slower than a snail. And so it's hard to really imagine how slow it is moving, how slow a conduction electron is moving. So it's somehow like, suppose I switch on and off the light. It's just like it turns on immediately. It doesn't feel like the electron move from here to there with 10 to minus 7 meter per second speed. But actually, that is the case because we don't actually have an electron moving from here to there. Actually, the electron is pushing the forward electron to go ahead, and then you will have the current. So here we defined a variable called the resistance and resistivity. So I suppose you should have learned it in circuit analysis. If we have applied the same potential difference between the end of geometrically similar rod of copper and of glass, very different current results. So the characteristic of the conductor that enters here is that it is electrical resistance. The resistance R of a conductor is defined as R equals V over I, R equals V over I. So this is the resistance, this is the voltage, and the current. The voltage or the potential difference across the resistance and the current going through it. So V and I are proportional to each other. And for a given material and geometric structure, the ratio is a fixed number. We call it the resistance. The resistance. So the SI unit for the resistance is of course ohm. And actually we know this formula is called the Ohms Law. So where V is the potential difference across the conductor, I is the current going through the conductor. So the next one is the instead of resistance of an object, we may deal with the resistivity rho of the material. So actually, resistance depends on the geometric shape of the material. So we want to get a variable which is independent of the geometry, only depend on the material itself. So this is called the resistivity. So rho is equal to E over J. So the E field and the J is the current density. The current density. If we rewrite it in vector form, it is something like this. So E vector equals the rho times the J. So for the physics guy, they will call this one the vector form of the Ohm's law. So they regard it as the same, but for 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 us, we seldom use this. We seldom use this unless you need to design something like the radio frequency circuit. Maybe you need to use the Maxwell equation. Otherwise, if you just solve the distributed circuit for some low frequency circuit, then you only use the circuit theory. You only use the lump circuit variable, the RLC, and the voltage current, something like that is enough. So, and also, we also define another variable called the conductivity, which is the reciprocal of the resistivity. So it is called sigma equals 1 over rho. So for the rho, the SI unit is ohm meter. So for conductivity, the SI unit is ohm meter, quantity inverse. So we just define several variables. So in this case, we can have a formula about how to calculate the resistance. Given the geometric object, the geometric topology. So resistance is a property of an object. Resistivity is a property of a material. So I just mentioned it in the previous slide. So the resistance R of conductor Y of length L and uniform cross section is R equals rho times L over A. So I suppose you may have learned it in high school. And actually, rho is the resistivity, and the L is the length of the resistor, and the area is the cross section. A is the cross section area of the resistor, which means that the longer the resistance it is, the larger the resistance it has, and the larger the cross section area, then the smaller the resistance. So it's somehow like there's a road and then there are many people trying to go across it. So suppose there's a road and then there are many people going that way. So if the road is wider, then the people are free to move. And if there are hundreds of people in the street, and then even some are just standing there, seeing somewhere, and then the people may have difficulty to go through the road. It's somehow like that. And if the road is longer, then the people will be more tired to walk through it. So you can just imagine the resistance is something like that. It is very natural. So the resistivity rho for most material change with the temperature. For many material, including metals, the relationship between rho and the temperature T is approximately by the equation rho minus rho 0 equals rho 0 times alpha times the T minus T0. So T is the absolute temperature in Kelvin. So which means that the relationship of the resistivity and the temperature is approximately linear. You can somehow see it like here. Actually, it is. You can see it is a little bit bent. Yeah, it is not actually linear, but for simple calculation, we just assume that it is a linear relationship between them, so that calculation can be easier. So I suppose in high school you may have learned this before, and the teacher usually tells you that if it goes to 0 degree, then there will be no resistivity, and no resistance at all. But actually, it is a little bit more complicated than that. It is somehow called a superconductor, and usually we need to go nearly 1 Kelvin or really hundreds of Kelvin. Yeah, so that some of the material may have the superconductor phenomenon, which means that it has no resistance in it. So 那些人喜欢把那个超导体叫做高温超导，但实际上它的温度是非常低的，它是接近绝对零度，接近了，就是可能是低于1度的绝对温度，那就是大概低于-272度啊。我有一个中学同学，他在台湾清华现在做那个量子技术的，所以他实验室里面有一些 chamber 是把那个温度降到了几百个 milli Kelvin 的温度，然后那些就会有那个超导体的特性。
高温超导不是指的是比液氮高的超导吗？
对，那实际上就是还是温度很低，他们就是希望把那个温度升高，但是如果你要
双层石墨烯这个高温超导，
实际上你要就是很多的他们如果需要到接近绝对零度的话，他们要液态氦，那他们尝试把温度升高的话，他们把那些叫做高温超导，但是实际上对于人来说，那还是很低的温度了。那我在大一的时候啊，就是大概17年前，那时候叫我化学的那个教授，他们说他们在实验室做了一个材料啊，然后他们是全世界第2名，把那个材料做出来啊，所以第1名那个拿到诺贝尔奖，他们就什么都不是了。
他们说双层石墨烯偏离一定的角度可以双层石墨烯偏离一定的角度可以实现高温超导。
所以呢？
所以就是高温超导。
你不能说的那么简单呢，反正他们就是找不同材料，他们有不同的特性，就是。
所以炒菜。
Okay, so this is a table about the resistivity for some materials at room temperature. So actually for For the upper part, you can see some of the metals. So you can see silver, copper, and gold, which has quite small resistivity compared with the others. And this part is the semiconductor. So for a electrical ECE student, you should be very familiar with the silicon. So you have N-type semiconductor, P-type semiconductor, and compare with actually for the silicon, for the pure silicon, it has a very large resistivity. But however, if silicon is doped with phosphorus or the negative ion, I can't really remember. So after the doping, the silicon to be N-type or P-type, the resistivity will be much lower, than the pure silicon, although it is still higher than the metal. However, the point we use the silicon is that we can control it. For metal, it is hard to control because you need to use the temperature control, which is not very flexible. However, if we need to control the semiconductor, it is more easy to control. And for insulator, for the resistivity will be much higher. So here is another sample problem. So rectangle block of iron has dimension like this. A potential difference is applied to the block between the parallel side in such a way that those sides are equipotential surface. What is the resistance of the block if the two parallel sides are 1 square n? Yeah. So first, consider this one. So which means this is a rectangular block. Yeah. So it's somehow like this. So 1.2 for these two sides, and then 15 centimeter for the other. So it's just a long wire. So the square ends for the two ends. So actually here the surface area is 0.012 square, which is 1.44 times 10 to minus 4 meters square. So the resistance will be rho L over A. So rho is 9.86 times 10 to minus 8. And then the length is 15 centimeter, 0.15 meter. So the area is 1.44 times 10 to minus 4. So finally, we get the resistance to be 100 mu ohm. So this is not mega. Careful about the. So we have mu 10 to minus 6 milli, small m to be 10 to minus 3, and the big M, which is 10 to the 6th power. So this is part 1. This one, 100 milli ohm. 100 micro ohm, which is 0.1 milli ohm. So for the second one, so two rectangular side with dimension 1.2 times 15 centimeters square. So which means that For the second case, we use these two sides. Somehow like this. So here A would be 0.012 times 0.15. So the area would be 1.8 times 10 to minus 3 meters squared. So the next one is R equals rho times L over A. So the rho is still 9.86 times 10 to minus 8. So the length is 0.012 over 1.8 times 10 to minus 3. So the 0.65 mu ohm. So in this case, the resistance is much smaller than the previous case because we have a much shorter length but a much larger cross-section area. So any questions? Okay. So we see the Ohm's law. So actually show how the distinguish among the device. So actually, which is nothing but V equals IR. There's too much to read. And actually, the resistance has a linear relationship between the voltage and current. However, there are some other conducting device. The current can exist in the device only when the polarity of V is a positive and the applied potential difference is more than about 1.5 volt. Where current does exist, the relationship between I and V is not linear. It depends on the value of the applied potential difference V. So what is this one? What is this one? Actually, it's a diode, I think. Maybe there are some diode with other property because as you learn a diode, it should have a 0.7 volt. Yeah, 0.7 volt. I'm not sure what is. Maybe the material is different than the characteristic may change. So for Ohm's law, it tells you that I is proportional to the voltage across the resistance. And yeah, it is quite trivial. So let's see another topic. It's about the Ohm's law in a microscopic view. 从一个微观的角度去看那个欧姆定律。So the assumption that the conduction electron in a metal are free to move like the molecule in a gas leads to an expression of the resistivity of a metal. If an electron of a mass m is placed in an electric field of magnitude E, so we have an electron of mass. So what is the mass of an electron? Very small, 9.11 times 10 to minus 31 kilogram. So it's placed in an electric field. So the electron will experience an acceleration. Yeah, because you learn it in chapter 21. You have the electrostatic force. So if you have an electron which has a negative charge, negative 1.6 times 10 to minus 19 coulombs charge, and then in an electric field, then you have an electrostatic force, the Coulomb force. So you have the Coulomb force and then the magnitude. So you will use the Newton's law of Newton's second law of motion. So that we have F equals ma, A equals F over m, and then F equals to QE, and then here Q is actually E. And then we only consider the magnitude so that we ignore the negative sign. So here we have drift speed is alpha tau. So we assume that the electron is initially stable, initially stationary there, and then it has an acceleration, so that we try to accelerate for time tau. Tau is the average time between the collision, average time before the collision. So you assume an electron is maybe here, and then here, electron here, and then it is initially stopped, and then you try to go to the next point, and then it collides with another electron, and then you go to another direction. So then you also assume it is initially stable, and then you go to. Although it's not really correct, but it is just a try to explain the Ohm's law in a physics point of view. So every time the time between collision are different, but it assumes the average time between the collision to be tau. So the average speed of all the electron will be Vd, or maybe half of Vd. But actually, this factor is not really important here. It's just trying to explain the phenomenon of Ohm's law, why the V and I should be a fixed ratio. So here we try to substitute A equals EE over M into here. So we have Vd equals this one. And then also, previously we also introduced J equals to NEVD. So we can substitute Vd into here so that J will look like this. And actually, E equals to rho J. So so after we rearrange all these terms to the left side and then swap the left and right, we can see that E equals to something times the J. So we see that M is a constant, E is constant, N is also constant maybe, and tau we are also assuming to be a constant. So we have this one should be a constant. Given a fixed temperature, then we will assume these two to be constant. Maybe, but not actually, I think. But it very close to a constant. So this one can help us to explain why the Ohm's law may be correct. So here we know that E equals rho J. So rho should be equals to this stuff, which means this case. So the assumption that the conduction electron in a metal are free to move by the molecule. So we have the rho equals to m over E squared and tau. Here n is the number of free electrons per unit volume. Tau is the mean time between the collision of an electron with an atom of a metal. The metal obeys the Ohm's law because the mean free time is approximately independent of the magnitude of E of any electron field applied to a metal. So you just try to explain the Ohm's law in a microscopic way. So here we have another sample problem with what is the mean free time tau between the collision of the conduction electron in a copper. So actually we just substitute. We just use the equation we just have, m over ne square rho. So m is 9.11 times 10 to minus 31. Okay, we have n equals 8.49 times 10 to 28. And then E is 1.6 times 10 to minus 19 square. And then rho is 1.69 times 10 to minus 8. So we can check all the number in table 26.1 and appendix B. So we have 2.5 times 10 to minus 14 second, which means we can write it as 25 femtosecond, which is very short period of time. So for part B, what is the mean free path of the mean free path lambda of the conduction of the electron? What is lambda for the conduction electron in a copper? Assume that the effective speed is like this. So it is very simple. It's just like lambda equals B effective tau. So S equals VT, S equals VT. So 1.6 times 10 to 6 power, and then tau is 25 times 10 to minus 15. So lambda is 14 nanometer. It somehow like makes some sense. Although, as we can see, there we have made many assumptions here, and then we may just ignore some of the factor. Actually, if you really consider this one may not be really correct. Maybe if you need to consider the FA speed, you need to take a factor of a half, something like that. But yeah, this really makes some sense because you can imagine the lattice of the copper. So the electron may go through some of the copper atom until it hit one, and then it try to it will go to another direction. So actually, 40 nanometer, close to I'm not sure, maybe tens or hundreds of copper atom, so that it doesn't need necessarily hit one after it may pass through some of the copper atom. So this is about 150 times the distance between nearest neighbor atom in a copper lattice. Thus, on average, each conduction electron pass many copper atoms before finally hit one, because you can assume the radius of a copper atom. Most of it are are empty. The nuclear only occupy the inner part, only occupy the inner part, so that the electron can pass through 150 atom on average. But it's just an approximation, so this 150 doesn't really important, I think. So here we talk about the power. So a circuit consisting of battery B that is connected by the wire, which assume we have negligibly resistant to an unspecified conducting device. The device might be a resistor, a storage battery, a motor, or some other electrical device. The power P, or rate of energy transfer in an electrical device across which a potential difference V is maintained, is P equals IV. P equals IV. I suppose you should have known it. And if you use the V equals IR, and then you can get three versions, maybe P equals I square V, V square over R, I square R, I square R, I square R, V square over R, IV. So for a resistance, for a resistor, then all of these three equations can be used. And if you really need to explain it in a physics point of view, and then you can see that du is dqv. So U is the potential energy. And then you can use U equals QV to substitute the variable. And then we know that Q dq equals I dt. We assume the current to be constant because Q equals IT. And then here we assume the current to be constant, so we have IV dt, so that we move dt to the left part. So P is du dt, and then U is IV. So for semiconductor are material that have few conduction electron but can become conductor when they are doped with other atoms that contribute charge carrier. So I suppose you have learned, you should have learned it in applied electronics. So I just go through it quickly. So more charge carrier available. So for the doping, so it makes the semiconductor have more charge carrier available. So for N-type semiconductor, it uses the electron as the charge carrier, and then for P-type semiconductor, it uses the host to be the charge carrier. So if it is a no charge, it's just like a positive charge. For a negative charge, it is a charge. It is a moving charge carrier. So this causes a decrease of resistivity with increasing temperature. So superconductor are material that lose all electrical resistance below some critical temperature, somehow like this one. So just now we have a linear relationship between the temperature and the resistivity, but some physicians just try to make it go very low temperature, so around 4 Kelvin, which is minus 269 degrees Celsius. So about 4K. So below some critical temperature, most such material require very low temperature, but some become superconducting at temperature as high as room temperature. So here's another additional example. So here, so the figure shows a person and a cow. Each radial distance, d from the point where lightning of current I equals 100 kilo ampere strike the ground. So this is the lightning hitting this point. So we assume all the current will go into every direction uniformly. So the current spread through the ground uniformly over a hemisphere, 半球体, center on the strike point. The person's feet are separated by a radial distance, delta r per 0.5 meter. The cow front and rear hoof are separated by radial distance, delta cow equals 1.5 meter. So this is the worst case. I will let you know why this is the worst case in the radial distance. If it is perpendicular to it, it may be better. So the resistivity of the ground is rho equals 100 ohm meter. The resistance both across the person and between left and right feet and across the cow between the front and rear hoofs is 4 kilo ohm. 4 kilo ohm. So yeah. So what is the current? What is the current I per through the person? Actually, it will go from his feet to another. Yeah. So actually, E equals rho ground J. So J would be I over J would be I over 2 pi r square, because it is only a hemisphere. So for the whole sphere, it is 4 pi r square. So for half of the sphere, so it's only 2 pi r square. So next, we calculate the delta V across the main speed. So so we use this one, integration of E dr, integrating from d to d plus delta r per. So we need to calculate the voltage difference. So here we have delta V. So actually now we can just substitute this one here. So actually we have many constant. So we can just factor it out. So we have rho ground I over 2 pi. And then we have d plus delta r per, and then we have R square dr. So it is nothing but rho ground I over 2 pi, and then we have 1 over R, and then we can substitute d plus delta R per d minus sign. So finally we have minus rho ground I 2 pi R, sorry, no, not R. Should be something like delta R per over d plus delta R per, yeah, something like this. Yeah, because d and d will be cancelled. D and d will be cancelled. So finally, we have I per to be delta V over R. So we substitute all the number into this equation. So the rho ground is 100, and then I would be 100 times 10 to the third power over 2 pi. Maybe we just take the absolute value. We only consider the magnitude of the current. So so delta R per is 0.5 meter. And then 60 R is 60 meter. 60. So 60.5. And then times 1 over 4K. 4K. So the final answer will be 0.05488. So the next question is, what is iCal? What is iCal? So actually, there will be a current going through the cow. Actually, we can just use the same equation here. We only replace delta R pearl by delta R cow, then it will be fine. So here we have I cow to be 100, still 100 for the row, and then the next one is I is 100K over 2 pi. So delta R cow is 1.5 meter. So 1.5 60 times 61.5. And then times 1 over 4K. 4K. So the current is larger, 0.1628. So compare with the guy is lucky enough, 0.05. So this is so 3 times larger. So which means that That's why I just tell you if it is standing like this, then it will be better. Then the voltage across its feet will be smaller. So here's another sample problem. Yeah. So what is the current in a wire of radius R equals 3.4 millimeter if the magnitude of the current density is given by this one, in which R is the radial distance J0, like this. So IA, we can use the integration JA dA. So we have 0 to 2 pi, 0 to R, and then JA is J0 R over capital R, and then R dr d theta. We'll use the polar coordinate because of the wire should be a cylindrical. So here we have J0, 0 to R square dr, 0 to 2 pi d theta. So that's this one will be R cubed over 3. This one is 2 pi. So we have J0 to be 5.5 times 10 to 4 times R is 3.4 times 10 to minus 3. And then cube over 3 times 2 pi. So it would be 1.338. So next one, we have another current distribution like this. So for this one, the outer part is larger, the inner part is smaller. This is the vice versa. So here IB would be 0 to 2 pi, 0 to R, and then J0, 1 minus R over R, and then dA is R dr d theta. So we have J0, and then 1 minus R over R times R dr, 0 to R, and then 0 to 2 pi d theta. So this one is, so the first term is R. So it will become R squared over 2. And then here we have R squared, so that we have R cubed over 3 and then over R. So that we have minus R squared over 3. And then this is still 2 pi. So this one will become R squared over 6. So we can just substitute all the number. 5.5 times 10 to 4. And then R is 3.4 times 10 to minus 3 square over 6 times 2 pi. So this will become 0.6678. So we still have the third one. So for wire section 1 of diameter D1, D1 is here. Section 2, D2 is half of it, connected by a taper section. The wire is copper and carry a current. Assume that the current is uniformly distributed across the cross-section area through the wire width. The electric potential V along the length L equals 2 meters shown in section 2 is 10 mil V. The number of charge carrier per unit volume. Number of charge per unit volume is equal to what is the drift speed of the conduction electron in section 1. So here we need to use first we need to use E2 equals E2 equals V over L, V over L. V is this one, the section 2, electric potential change V along L, so that we can calculate E2. So here 10 mil over 2 meter, so it is 5 mil V over M, or you can write N over C. So J2, so we can calculate J2 to be E2 over rho, E2 over rho. So it is 5 mil over 1.69 times 10 to minus 8. So this will become 296 ampere per meter square. So this is J2. And suppose that we have the KCL, which means that the I remain constant here, which means that J1 A1 equals J2 A2, which means that J1 should be J2 A2 over A1. So J2 is 296, A2 should be 2R pi R squared, which means that we have A2 to be 4 pi R squared. And then for A1 should be pi R squared, which means it should be 16 pi R squared, because we use this one to calculate the surface area. So that J1 should be 74 A per meter. And finally, we can calculate VD to be J1 over NE. So J1 is 74 and N is 8.49 times 10 to minus 28, and then E is 1.6 times 10 to minus 19, so finally, VD should be 5.44 times 10 to minus 9 meter per second.